sessions if needed.
Yeah, you normally can't see this, but this wall is different now.
Do you practice? Hi Amir, how's your fun? Does any one of you practice Zoom software?
Yes. Yeah. I have used it.
So, you know, there one can put background behind you and set it up as you are on the beach or on the San Francisco bridge or whatever. So Steven, you can replace your wall with by using Zoom, having some setup backup.
Yeah, good idea.
Okay, so who we are and what are we doing? We are going a little bit on different pace than in normal years, but we have a good excuse with the circumstances. And our main goal is to get practical skills in WASP, and I will invite everyone to use it towards projects very soon. Of course, if someone wants to use other software like Gaussian or maybe some molecular dynamics, it is fine, but I will provide instructions and help at most for using WASP. We progress a little slower than original plan. Yesterday, most of us did learn, did obtain confidence in getting density of states out of WASP calculations. Next steps, next closest step will be very similar to what we did in Gaussian, to plot orbital total charge density, consider spin polarization, and right after that we will have at least two more sections, two more subjects. Hi, Yang Chao.
Hi.
So we will have two sections that we didn't practice in Gaussian: absorption spectrum and molecular dynamics. So this will be key features used for the project, and also there will be a little thing similar to Gaussian. We will learn how to change charge and multiplicity in WASP. In Gaussian, it is just two numbers. In WASP, they are also two numbers, but one needs to type some keywords in front of them. So let me share the screen. It should come up. Okay. Yeah. Now it may create the set of images, which is always a fun to see this recursion. So I did send a link to PowerPoint file in Google Docs. So it's called like Google Slides. Small document. It is different from today's lecture, and I suggest I want to check if you can open this document, and if all of us who are connected can edit this document simultaneously. Please try to open it, because it is the practical part of our today's meeting, and I also want to learn if you can do some collaborative thing, replacing the standard Blackboard and getting full functionality through online meetings. So I do see, okay, I see 2 people connected. So at least someone can connect. So please keep trying, and you do see here list of subjects, and I suggest we start voting for presentation subjects. So please try to type your name after the subject that you think will be near and dear to your heart. Like click and we can vote by voices, but if you type yourself, probably it will be most optimal.
Dr. Killen?
Yes?
I believe the link you sent us is a view only. We have to request to edit access.
Okay.
I have sent you a request now.
Oh, thank you so much. Anyone with a link can edit. Yeah, many thanks for bringing it up, Steven. Okay, can you edit it right now? I think I granted access to everyone.
Should we email? Dr. Email?
Yes.
No, please try to type right in this Google Docs document online. Not downloading, but just open it and type. Yes, I see someone is already typing. It doesn't disclose your names. It right now I see Anonymous Llama is trying to type near the UV's spectrum.
Oh, I believe that's me.
Steven?
Yes.
Okay. Excellent. Thank you. Thank you for the vote.
But how can I type in your drive?
Let's please help each other. If anyone can explain, maybe you will do it quicker than I do. Just speak up and help each other verbally.
So you want to check to see if yours is view only. It shouldn't be now, but once it's in edit mode, you just have to click next to where you want to type, and it should appear with a cursor, and then you should be able to type.
I'm opening this on Google Drive. Okay, I clicked. It appeared only.
I'm going to.
I don't see the option.
Raju, I'm going, and everyone, I'm going to go away from this, from displaying this slide. Although you can keep typing there. I will just show how I was opening it. So here is my Google Drive.
Yes.
So I click on this document. It opens in this way, and then it shows open with Google Slides.
Yes.
So I open with Google Slides.
Yeah.
And then it should be editable.
Okay.
Okay. Yang Chao selects DOS. Raju selects WASP input. Okay, I see. And Amir also wants WASP input. Well, keep. If you want more than one type, and then we'll discuss it. Do not hesitate to write more than one. Okay.
Oh, Amir changed. So I
Uh,
think I
okay. Amir agrees. Zhaofan, thank you. Um, I I think the best choice. If I would be in the class, I would select either my primary choice will be 8 as Zhaofan, and my second choice will be number 2 as Yang Chao. So, do we have only 7 people today?
think Salim is not here.
Okay, then
Thermal heating wait for Salim.
candidates for thermal heating are Salim and Gvender. But thank you everyone for making these choices, and I'm very happy that we can practice online interaction. I think we can even maybe write some documents together as this software was designed for collective editing. Okay, I'm going to show the second part, and this will be a quiz intended for the end of the meeting. So on the left, on the right, there are boxes, and in the middle there are spaces. So by the end of the meeting, we should be able to distribute these little boxes over empty spots. And it will be an algorithm similar to Hartree-Fock and similar to optimization. So it is how the WASP software is working. So the ultimate goal of the meeting is to fill these boxes in the educated way. And when we'll go over sufficient amount of material, I will invite everyone to go here and maybe move the boxes one person at a time. Okay, I'm removing it from the primary. Oh, it's answer. I shouldn't show it. Let's go to the beginning of the meeting. Let me check that no one is irritated by the fact that I am showing the navigation panel. So it is not a full presentation mode, but the navigation panel is on the side. Is it okay? At least I do not hear big objections. Okay. So we are in the oh no, we are past the Hohenberg-Kohn theorems. We are in between 20 and 21. We are looking for Kohn-Sham algorithm and flow chart of DFT computation. And you have the slides, and you see here are the links for the lectures from previous years. So if you think your instructor is not performing well this year, you can look previous years and get some backup. Those are spin polarized density of states that we will cover a little later. We are behind that. And those are possible research directions that we will need to choose as soon as we complete presentations on VASP that you have elected today. So please lean back, relax. I will let you know when you need to really focus. I will be entertaining you and going over review of old information, and I will attract your attention when there will be really important things. So we are doing density functional theory because we want to model materials and their properties. There are two theorems. One is that density determines only one potential, only one wave function, only one molecular Hamiltonian. And second DFT theorem is that if one knows absolutely correct density for the ground state, then energy as a functional, symbolized by these round brackets, of the correct ground state will be smaller than energy of any trial density, any density that deviates from ground state density. Basically, it's same as a variational theorem, and it will give us background to go over iterative cycles. So when we were meeting last time, we were going over the concept of functional derivative. So the increment of density in certain area of space times potential gives increment of electron to nuclear potential energy. And if we make a fraction out of this, oh, you do not see my mouse, so I need to keep drawing. And if you make a fraction of these two things, the external potential and density, then it reproduces the potential. So with this functional derivative, we are almost ready to set up iterative calculation in the same way as we did in Hartree-Fock. But there is a missing part. There is a missing part, density, that we will start from when I finish the review. So another concept that Raju was objecting 2 days ago, and it is very natural. I'm very happy that we introduce an auxiliary world where electrons do not interact to each other, and then we set up a constraint. We set up that there is a, we assume that there is a mathematical procedure that allows to continuously change the strengths of electron-electron interaction from 1 to 0, and at the same time one modifies the energy contribution from external potential from interaction with nucleus in a such way so that summation of these two will stay the same. And if one accepts this assumption, then one can perform all calculations in this auxiliary world, where electrons do not interact to each other explicitly. I'm not telling that electrons do not interact to each other in our world. we have a transition from our world to this auxiliary world, and in the auxiliary world, the electrons do not interact explicitly, but by performing a transition from auxiliary world backwards to ours, we get electron interaction back. It is just a computational trick. So we do not abandon electron interaction. Okay. And this little, not little, this capital T is kinetic energy. There are no theorems requiring to treat it based on orbitals. One can treat it based on the density, but we will use concept of orbitals just because it is very comfortable numerically. I do not have the book in front of me, but I know that Anil was always asking. Right now, I'm following the Ira Levin textbook in quantum physical chemistry, quantum chemistry, Ira Levin. Levin. I will try to bring this book or front page to your attention if some of you are interested. So it is not the original book by designers of density functional theory, but there is a very good chapter, very good digest of the theory in this book. Okay, I'm yet continuing the review of what we did last time. So, if we are inside our auxiliary world, then the external potential can be expressed as subtraction of total energy minus kinetic energy. And then we can plug this expression into functional derivative of this external potential over density that will bring the one electron potential. So we have functional derivative Greek delta over Greek delta rho of total energy minus kinetic energy. So the very beneficial and helpful benefit of this equation that we set up, it is a step towards feedback loop. So from total density we set up potentials that can be used to find one electron orbitals. And then from this one electron orbitals later on we will find potential. I also let me attract your attention to the orange level of alert. It's not the red, not most important, but please keep an eye on equations because some of them, like the last one on this slide, will be explicitly used in the Kohn-Sham DFT algorithm in the quiz that we will try to complete at the end of the meeting. Okay, I'm going to the next slide. It is still repetition, recall of what we did last time. So the external potential is the same for each electrons, and kinetic energy is just summation of kinetic energy for each electron. Therefore, big Hamiltonian for many electrons and I bring it up to the attention once again, we are in the auxiliary world where electrons do not interact with each other. So from multi-electron Hamiltonian, we go to summation of partial Hamiltonians for each electron separately. Since electrons do not interact with each other, this is very possible. And this lowercase Hamiltonian is composed of kinetic energy and this external potential, because it is the only thing that acts on an electron in this auxiliary world. There is no interaction with other electrons. Interaction with other electrons are hidden in the transition between auxiliary world and the real world. And then this little lowercase h acts on the theta, which is here in books it is typically used for Kohn-Sham orbital, one electron orbital, equals energy of orbital times orbital itself. So it looks like one electron Schrödinger equation. In order, I would like to focus your attention maybe at an orange level to this equation, because it will be also used in the flow chart that we need to accomplish by the end of the lecture. So as soon the equation from last slide is repeated here. So lowercase Hamiltonian acting on the unknown orbital theta gives unknown orbital theta times eigenenergy of the orbital. And as soon as we know the orbitals, we can form a Slater determinant and find overall wave function. Although overall multi-electron wave function will not need it in any step of the density functional theory procedure. It is just a knowledge that we can construct it. Okay, so I'm done with review what we did, and we need to complete some leftover from previous lecture. Specifically, let me bring up the goals, and let me also correct the typo. Where is the assistant? So the goal is to set up a procedure that will generate the density. We do need to construct density out of orbitals if possible, because density determines energy, and density is explicitly needed for the functional derivative. Thank you for the assistance. Okay, and the text in red here is just summarizes what I was telling. So let's go slowly but surely. The density is defined in the same way as probability density. So density of charge and probability density are two alternative interpretations of quantum theory. In case we have a wave function that is composed of many electrons, we just need to take this absolute wave function absolute value squared and it will be a density that depends on so many independent variables as the number of electrons in the system. This is correct. This is cool, but it is not what we need. In this definition, density is defined on too many independent variables, and we will lose most of the benefits that were originally promised for the density functional theory. We need charge density in certain point of time integrated over all electrons. We need an argument, we need a function we need a density as function of only one Cartesian position in space. So the first line is the same thing. Density as function of many variables as a product of a wave function conjugated to the wave function itself. This is not what we need. We need dependence only on one variable. If we want dependence only on one coordinate in space, we need to do n minus 1, where n is number of electrons, integrals. So we need to integrate over position of second electron. We need integrate over position of the third electron, and subsequently we do integrations of all but one electrons, including the last one. I am not going to make mathematical proofs, but I invite you to practice this procedure for a case of wave function consisting of two independent variables. So let's assume that we have solved Kohn-Sham equations with this lowercase Hamiltonian, found two orbitals, and placed electron 1 and electron 2 on these orbitals. We can form many electron wave function as a Slater determinant, 1, 2, minus 2, 2, 1. And then we will plug this Slater determinant into first line and then into the second line, and just see what happens. I assure you that you will not regret the result, and so you will enjoy the result, and it will be beautiful. So let me move to well-typed equations. So in the definition of the wave function, we need to practice Slater determinant that you all like, right? So we do orbital number 1 where with first electron times orbital number 2 with second electron minus orbital number 2 with first electron times orbital number 1 with second electron. And in case we need the complex conjugate, we just put star in front of each orbital, right? No one objects. Okay, good. Now let's use these two equations and plug them into this definition. So since we have only two electrons, all but one means integrating over position of the second electron. In very few minutes, you will see that it does not matter which electron we integrate over. We can put R2 here and make integral over R1. The result will be the same, and it is the result will be very symmetric, very beautiful. So let's go over this integration procedure. So we multiply wave function with star times wave function without star. So it is the natural desire to open brackets. If we multiply two factors, and each factor consists of two terms, how many terms will be in the outcome? 2 times 2?
4.
Yes, thank you. Thank you, Rebecca. So if we carefully do it, so each term will consist of 4 orbitals. First 2 orbitals will be with conjugation, and second 2 orbitals everywhere will be without conjugation. So let's, I'm going to copy paste previous equation here, otherwise we will lose track. Okay, so we are going over the first 2 times first 2 in the second term. Then we are getting the first 2 with star, minus sign, second pair without star. Then we are getting the second pair with star, with minus sign, times this sign first pair without star. And last term we get the second pair with star and second pair without star. And because they both have minus, overall sign is plus. Okay? Now, we do need to perform integration over variable R2. Which property are we going to benefit in this operation? It is a standard property that we are practicing when we need to get rid of the wave functions.
Delta.
Which one?
Delta.
Yes, orthogonality, right? If we integrate theta I of R times theta J of R dr, then it will be 1 if I equal j and 0 if I is not equal j. Make sense? No one objects this property, right?
Yes.
Good. Now let's identify if any of these orthogonal wave functions are popping up in our long expression. So here is R2 and here is R2. It is applied, and in this general properties there should be star. So the index subscript of the orbital that depends on R2 is the same. Therefore, integration over R2 will remove this theta 2 because their integrated product will give 1.
Yes.
Okay? So it will be 1 times theta 1 of R1, theta 1 of R1. Now let's go to the second term. Here is R2, here is R2. The indices of the orbitals are different. Therefore, right, it gets 0 and the overall term is removed, right? Now let's look on the third term. Here is R2, here is R2, and the indices are different. So due to orthogonality, it will be 0. So this term will be removed as well. Okay? And in the last term, we have R2 and R2, and the indices are the same. 1 and 1 here, which means the integration will be equal to 1. Then we can remove the orbitals that depend on R2 and keep only things that depend on R1. And also, as a result of this operation, we do not have the integration anymore. So no integral and no dr2. So we will have only stuff that is stored in these blue boxes. Theta 1 R1, theta 1 R1, plus theta 2 R1, theta 2 R1. This is a very, very beautiful and useful expression. Let me try to verbalize it, not by equations, but by words. So we scan over all available orbitals, and here the orbitals are only 1 and 2. We explore these orbitals in the point of space corresponding to our independent variable R1, and we add together probability distributions contributed by first and second, and so as many orbitals are as we have in this Slater determinant. So the expression that we have just proved is as follows. So we have first orbital squared plus second orbital squared, and it will be total density of charge of overall system. This is absolutely, I do not hear sounds of extreme happiness, but I'm very confident that you will realize it and you'll celebrate this observation later. So the total density of the system with so many electrons is just summation of orbitals squared, of all occupied orbitals squared. This is really cool. By this equation, we get rid of multi-electron wave function, and we can do all calculations like several orders of magnitude quicker. And by theorems, we know that these calculations must be correct. If the total number of electrons is big, instead of writing this summation, I can write for summation sign I equals from 1 to highest occupied orbital, or instead I can write here number of electrons divided by 2 if it is spin restricted case, and then adding together all orbitals evaluated at the space point R. So orange level of alert to focus. I'll use the orange highlighter. So please observe this equation as it is an important part of the Kohn-Sham procedure. So this is a component that helps to go from orbitals to charge density. And charge density is used in the functional for energy and in functional derivative. Okay, now we are done with our last lecture, and we can start new lecture if if you have Steam. I understand that. Let me ask how energetic you are, and do you need to leave to disconnect literally at noon? If you have something scheduled, huh?
I do, Professor. I have to leave it.
Okay, okay. So I'll speak for another 5 minutes, and then we'll continue on Tuesday. So there are several key equations for density functional theory. And before we go to equations, I just let's bring them as concepts verbally. So total energy, that is later set up as a simple formula. And we have seen how total energy can be expressed of density in the Thomas Fermi theory. Then we do have a external potential that is expressed as functional derivative. We do have one electron equation for molecular orbitals, and we do have a protocol to compose density out of orbitals. So those, like, we are cooks in the kitchen, we are wet chemists in the wet lab. We do have these components, and we need to cook them together into a theory that works. So the equations, I'll probably bring them when they are typed in a better way. So total energy as function of density, potential function of derivative over density, one electron equations for molecular orbitals, and the protocol how to compose density. We are going to use the same language, the same notations as programmers use before writing the code. So oval for input or output, arrow for data transmission, square for mathematical operation, and diamond for branching, for decision, for condition. Okay, let me bring back the Google Drive document. So on the left panel, you do have all components, and you have the round part for input and output, and you do have the diamond for condition, and all equations. So since Steven needs to leave, let's give him a chance to give the first choice. So please click on the box that you prefer and move it to the space where you like. Okay, excellent. Thank you, Steven.
Yep.
If you need to leave, feel free, and I hope the recordings will be available. So who is next?
Easy.
Raju?
Yeah, I can do the work.
Okay, please do.
Let me do the hard part.
Okay.
Just a second.
Excellent, excellent. So you see, many thanks to Raju. He used benefit of pattern thinking. So it is the same pattern as we used in geometry optimization and in Hartree-Fock. So checking with tolerance limit is condition of convergence. If it is maintained, then we go to output. If it is not, we repeat the procedure. Who is next? Mahek? Excellent. Thank you. Thank you, Mahek. It's also benefit of pattern thinking in a very good sense. So we start from input and we end with output. As soon as right. Very good. Very good. Now,
I can provide some for input.
Okay. Who is that?
It should be here.
Yes, yes. Amir, thank you. And Amir is bringing up a very important idea and component. Before we start cycle, we need to get densities.
We have the initial density.
Exactly. We need an educated guess of a density. And in VASP, one can take this initial guess as random numbers. You will later see that even if you start with random distribution of density, the procedure is so perfect that it will get correct answer anyway. But to make this protocol running, one needs initial density. Good?
Yep.
Yes.
So after we do have density, who is next? Rebecca, would you like to try? Who was it? I do not see it by names.
Yang Chang.
Okay, Yang Chao, thank you. So yeah,
Thank you.
this is very reasonable. So we the order of these steps is not as critical, but you need to have a potential in order to practice one electron Kohn-Sham equation.
Yes.
Okay, who is next?
The next chance is 50-50.
Yes. So who was doing this operation?
I was.
Oh, thank you, Rebecca. Yes, correct. As soon as we have lowercase v, external potential, we can plug it into Kohn-Sham equation and find orbitals. And now for Zhao Fan, there is no big intrigue.
100%.
100%.
Right. And
Win-win game.
I'm missing one box and one step to compute energy. As soon as you have density, you can compute energy anytime, and we can add a little box between this and diamond. But I would like to congratulate you all. As a class, you did a brainstorming technique and you redesigned Kohn-Sham procedure of density functional theory. So each of you are now certified algorithm designer, and if you can just hire some professional programmers and teach them how to write a code that will do density functional theory calculations. So it's really cool, and now you get a general idea how VASP software is working. Okay, very good. Let's see if I did similar, better or worse in previous years.
The VASP also is available on CCAS, Dr. Kilin, do you know?
If you have active license,
Yes, it is.
yes, it is.
But yeah, but you have to have license, otherwise you cannot use.
And
okay.
and they will not allow you to use it without license. They do no exceptions. So
Okay.
we are about to end, but before we end, I want to impress you most strongly. One big impression. There are three big impressions from today. First, how nicely density is composed out of orbitals. Second, impression that you guys are able to generate algorithms. It means you are progressing really well in the course. And the third impression, a little intrigue, you will see it in a minute or two. Remember our first algorithm when we were going over geometry optimization or molecular dynamics. Do you remember this flow chart? So when one starts from geometry, one computes the potential energy for given geometry. Then one computes gradient and step, optimization step, makes an increment, computes energy at incremented step, and checks whether it is within tolerance limit. If it is yes, then geometry is optimized. If it is no, then one goes to the next iteration. Do you remember it? Okay, yes. Good. Now, in this algorithm, we did use U capital as of R capital, right? Potential energy as function of the positions of ions, right?
Yes.
Now let's merge two theories. In our previous slides, you have designed an algorithm how to find total energy of a system if the positions of ions are known. I'm going one slide back. So if positions of ions are known, you can compute total energy as function of positions of ions. Can we plug in this algorithm inside the box where we need to find total energy? Yes?
Yes, yes.
Yes, yes, we can do that.
Yes, I agree. So in this black box, which before we didn't discuss where we get this potential total energy. Now I just redraw it as a bigger box, and in this open space I am going to plug in the Kohn-Sham algorithm. Now you are ready to write software analogous to WASP or Gaussian. So you do optimization cycle for geometry, and inside each cycle for geometry you have another cycle for electronic structure. And if you are looking through outcar at the beginning, or file OZCAR, it shows, I will bring it up on next lab, that it shows external cycle where energy is, geometry of ions is optimized, and inside each ionic cycles there are little electronic cycles. So this is exact implementation of this two loops algorithm. Okay, I'm a little off with numbers. I think we are done with lecture 20, but we are done. I'll stay here to answer any questions, but the meeting is done and everyone is welcome to depart or disconnect.
Okay, thank you very much. Have a good day.
Thanks, you too.
Thank you.
Thank you.
Thank you, bye.
Thanks.
Thank you.
Everything is in.
Yes, yes, Raju.
Can I talk to you on Skype a bit?
No, we can talk it on this connection. I will stop recording so that what we